So thank you for the introduction, Arne. Yeah, so my talk will be about the latest flow solver improvements that we did during the last year. And we had a special focus on solver accuracy. So almost all topics I will present will have something to do with enhanced accuracy. But before I'll start, let me give you some motivation. What you see here is a graph from a pattern from a shell. And what you see here on the x-axis is the permeability that people have measured. So they did measurements on different types of rock samples with different permeability range. So you have like highly porous rocks with high permeability, and we have low porous rocks with low permeability. And on the y-axis you see the simulated permeability. And as you can see, not all simulation results are on the ideal line. So if permeability are on the diagonal, the simulation and the experiment would agree, but this is not the case for rocks with low permeability. And there are several reasons for it. For example, the RAV is maybe not always satisfied. You have the segmentation is always an issue. But also one of the issues is the limited resolution and also numerical discretization techniques that are used for the simulation. And about this topic, we can do something. And yeah, so during this talk, I will show you the latest improvements that we did to get the simulation and experiments closer together, also for the cases where this was not the case in the past. So the first topic will be about sub-voxel resolution. So one of the solvers for flow is the Lier solver, and the Lier solver has the special feature that it uses an adaptive grid. So the adaptive grid is used to discretize velocity, pressure, but also other quantities like potential or displacement in the other modules. And previously, the smallest computational cell was 1 voxel. But one cell could also be more than 1 voxel, as you can see on the right image. Usually you have very high resolution, so you have the smallest cells at the solid interface or in places where you have strong gradients. However, it was not possible to have cells smaller than the voxel length. The only way you can do this you have to rescale the structure in GeoDict and then give it to the solver. But the solver could not do it by itself. But why is such a feature important? So let me give you another example. So imagine a 1D pipe. You have 2 parallel plates, and for this, for such a simple structure, you can compute the exact permeability. So for a channel with 1 micrometer gap, you know the exact permeability. Here it's like 2.7 10 to the power of minus 14. And if you resolve this with this structure with just one voxel, and then when the computed permeability is 8.3, so you have an error of about 200%. But if you now give the solver a structure where the gap is resolved with 10 voxels, the error drops down to 2%. So as you can see, resolution matters for the accuracy, but you need a lot more cells to get high accuracy for this case. But the solver already has an adaptive grid, and the solver should decide by itself where to refine. And this is now possible. So now, as you can see in the image, it is now possible that the solver can introduce cells smaller than the voxel length automatically. So you can exchange runtime and memory for higher accuracy. But this feature alone is not sufficient, because the solver has to know where to introduce new cells and where to use the sub-voxel feature. And To do this, we also implemented a new criterion to predict where new cells should be introduced, and this is called posteriori error bound. You may already know the error bound stopping criterion, and this works like it tries to predict the final solution, and the solver stops relative to this prediction. And we do something similar also here. So for each voxel, we use like higher order polynomials to estimate a better approximation, or to have a better approximation, and we compare it to the actual values. And if this differs more than a certain threshold, then the solver will introduce more cells. And yeah, this feature is very important for flows. For example, if you have structures with low porosity, with small pore channels. But this can be also important for other application areas. For example, for filtration, where you have like a dense filter cake on the top. And this can also be very important for computing relative permeability, where you have low saturated states and you have like thin layers which are not resolved well enough. So that can be very important. And for future application, it can also, sorry. For example, the Lier mechanics solver will also get this feature in the future, and where it can be very useful, for example, for foams, where the structure is resolved, where you have very thin struts and walls, where the solver can also increase the accuracy automatically. So let me show you some results. Here you can see the 1D channel again. And what we do here, on the y-axis, you see this posteriori error bound, which I already mentioned. So what you give here as a user, you can now prescribe the desired error. And in this case, it is the error with respect to the analytical solution. And on the y-axis, you see what you actually got from the solver. And in an ideal world, the red curve would be on the diagonal, or it should be at least below. And for this simple case, we almost got a perfect result. So for many user inputs, we are on the diagonal, and for the other ones, we are slightly below the ideal line. So here it works almost perfectly. Let me also show you another example where you can more see what happens here. We have like a slit structure with 8 × 8 voxels, and we also have here like a slit with 2 voxels in diameter, and we do like the same experiment. So I prescribed some errors, and then I measured what accuracy I actually got. And on the bottom, you can see what happens if I prescribe different posteriori error bounds. The solver starts to introduce sub-voxel cells in the slit and also around the slit. So the solver starts to, when you increase, or if you want to increase the accuracy, the solver starts to introduce more and more sub-voxel cells in the center of a slit. And here it also works very good. But now let me come to like a more real example. So what you now see here is an acetylate carbonate rock structure from a digital rocks portal. And here we use the crop out with 700 × 700 × 700 voxels. It has very low porosity, and in the percolation path, it just resolved by 5 voxels. And here we did like a similar experiment. So we varied the error bound, and we computed the permeability. And what we also did here, we resolved with a structure with a lot of voxels. On the bottom table, you see like a reference where we increased the resolution with a rescaling feature in GeoDict and used a regular grid to compute like a reference solution. And and then we used the sub-voxel feature, and we compared And you see that when you increase the accuracy, when you increase the error bound, if you reduce the error bound, the computed permeability gets closer and closer to our reference solution. But of course, with exchange, it takes a little bit more runtime and more memory. But the results are also quite good here. We also want to do faster flows in GeoDict. And maybe this mesh refinement criterion is maybe not ideal for fast flows. And we had the idea to use like the local Reynolds number to decide where cells should be split. And here you can also see the definition of a local Reynolds number. So it depends on the voxel, or on the cell size, on the density, the magnitude of the velocity, and the viscosity. And the second new mesh refinement criterion splits a cell if the local Reynolds number is higher than the specified threshold. And you can also combine this mesh refinement criterion with the posteriori error bound criterion. So you can combine both and test what works best for your case. And here you see also with 2D examples again, the slit structure, where we have like a fast flow with, in this case, a Reynolds number of 5. So you get like a high speed velocity tail behind the slit. And what we did here, we varied this local Reynolds number that you can specify for the mesh refinement, and we computed the pressure drop. And at some point if you decrease this Reynolds number threshold, the computed pressure drop gets closer and closer also to the reference solution. And here the reference solution was also computed with a very high resolution variant of this structure. So the pressure drop also converges here properly to the reference solution. But here you have to specify, you have to know the Reynolds number you have to give to the solver. And so this may be not that user-friendly compared to the posteriori error bound. But we will work on this also in the future. We also applied this mesh refinement criterion to a more realistic example. So here we have a weave structure with high speed flow with 3 meters per second. Here the Reynolds number is 40. And here we have a weave and flow goes from top to bottom. And here we also did a similar experiment. We have a reference solution where we used we use a high resolution variant to compute a reference pressure drop. And here we now also varied this Reynolds number threshold and computed the pressure drop. And here you can also see that the computed pressure drop converges properly to the reference solution. Here the runtime increase is not that significant, and also memory increase is not that significant. So this criterion can be very useful for high-speed flows. Yeah, but we also want to compute faster flows. In the previous example, we had like a Reynolds number of 40, but we also want to be able to compute flows for much higher Reynolds number. What you can see here on the right side is a simulation that was done with a simple FFT solver some years ago. And the simple FFT solver has a special like feature. It uses a fast Fourier transformation to solve the so-called pressure correction equation. And it uses like an explicit scheme to solve a momentum balance equation. And there's like a relaxation value that you may already know, which is available in the solver tab. And you can correlate with relaxation value with a time step. So you could do something like time-dependent simulation with a simple FFT solver. With a Lier solver, it's a little bit different. So it also has like an explicit scheme, but it cannot solve a pressure correction exactly for each step. And Valier solver has many different optimizations built in. For example, the multi-grid method and the bi-CG step method that you can also use. And then the intermediate computational flow fields cannot be seen as time steps. So if you want to really do a transient flow simulations, we have to solve a transient Navier-Stokes equations with Valier solver. And in GeoDict 25, we did like first steps towards this. So yeah, so like in the short term, we want to be able to do direct numerical simulation, as it is called, where we solve a transient Navier-Stokes derivation directly, and here also the vortices are resolved directly. In the future, we also want to implement one of the turbulence models, for example, a large eddy simulation, to be able to also simulate much higher flows with a good accuracy. Here's also, so as I mentioned before, we did some first steps to do transient Navier-Stokes simulations, but we are not yet finished with implementation. We have just started, but I already want to show you some first results. So here you see a benchmark. Here I will produce the common vortex treat. So the common vortex treat is like a phenomena that you see for very fast flows, which passes an obstacle. In this case, we have a spherical obstacle, and if the Reynolds number is high enough, so if the Reynolds number is not extremely high, you get like two vortices behind the obstacle, as you can see on the left image in the center. But if a Reynolds number increases even more, then these two vortices are not stationary anymore, and they will move over time, and there will not be and there is no stationary state. So the flow field will always change with time, and this vortex will like split and will move from left to right. Yeah, and on the right you see some simulation results. The colors indicate here the vortex strength and not the velocity, as it is usually done. So here we visualize like right-handed and left-handed vortex strength. And we compared it with, for example, in this case, we compared it with a COMSOL. And we can really nicely already reproduce this common vortex treat. In the future, we also want to do more in that topic, and we are also doing more benchmarks, but due to the lack of time, I cannot show you these results. So now I come to a different topic. Another way to increase the accuracy is to do something with a numerical scheme. And one thing that governs the computed permeability is the no-slip boundary condition. And the no-slip boundary condition can be implemented in different ways. And we added two new no-slip boundary conditions for the simple LFT and Valier solver, which are available for the flow simulations. The EJ already had this no-slip boundary condition implemented, but the options was like a little bit hidden. And now we made these options easily available, and now all solvers support this no-slip boundary condition. And the first one is round corner and sharp corner. So you can choose between the two. Round corner is what the solver by default already used in the past GeoDict versions. So here you see the slit again, but the slit ends, and here you have a corner. And what you can do here, you have now the freedom to choose where the no-slip condition should be applied. And in the center of the slit, it's clear you want the no-slip boundary condition right at the no-slip interface on the left and right side of the wall. But what should we do after this corner? And now we have two options. The no-slip boundary condition can be enforced really at the corner, as you see on the bottom. And you see how the flow profile looks like if a no-slip condition is not applied at the corner, but in the center of a face right after this corner. Yeah, the round corner is ideal if you have like round structures, for example, fibers, also grains. And this sharp corner can be very interesting for like rocks, because in rocks we usually overestimate the permeability, as you have seen in my very first slide. And here it can be very useful to get closer to the measurement. And this feature does not introduce like more runtime or memory. So memory is the same, runtime is also almost the same, so you get like additional accuracy for free. The other feature that we have implemented is, so now we have the option between choosing first and second order discretization of no-slip boundary condition. So previously we used like a first order approximation to enforce the no-slip boundary condition at the walls. And now you can also choose a second order approximation, which gives you also more accurate results without having more runtime and without using more memory. And I also want to show you some results here. So you see this 1D channel again. So on the x-axis, you see, so we have resolved this slit with different resolutions. So from left, you have lowest resolution, just 1 voxel. On the right, we used, for example, here 8 voxels or 10 voxels. And on the y-axis, you see the error with respect to the analytical solution, which is available also for the 1D channel. And the red curve is if we're using the first order no-slip boundary condition, and the blue curve is using the new second order boundary condition. And you can see that we need much less resolution to get the same accuracy. So here, in the beginning, I said that if you want to have like 2% deviation from the exact resolution, you need 10 voxels in diameter. With the second order, here you just need 5, so just half of it. And on the right side, you see another example where we have a staircase-like a structure. And here we assume that the staircase is the exact geometry. And here we combine the different no-slip boundary conditions. So you have like 4 curves. And you see that if we're using a round corner and first order, it converges slowly to the exact solution. If we now combining second order and sharp corner, you get almost the exact solution with very low resolution. So it's an ideal condition for this kind of structures. So, but now we also tested it on more realistic examples. And on the left side, you see again the acetylate carbonate structure with lower porosity. And here we used a crop out with 500 voxels cubed. And here we did an experiment. So we took the 500 voxels cubed structure, and towards the left, we downscaled the structures. So with process geo rescale, you can shrink. So and here we did it from 500 cubed to 125 cubed. So and when we did the flow simulations. And in the other case, we also upscaled the structure. So we assume that the voxel represents the exact geometry. We rescaled the structure. And and now we also have a reference solution with a very high resolution. Here we used 4000 cubed version of a structure to compute a reference solution, and we we compare now here the first order with round corner, which is the wedge curve. And if we're using second order and sharp corner, it converges just much faster compared to the first order and round corner variant. And even with 125 voxels, you are quite close to the reference solution. And on the right side, you see results from there's like a benchmark paper from Shell where they measured 12 different flow solvers, and they applied the different flow solvers on 36 different types of structures, and they were also for rock structures. And what you see here in gray is like the average permeability computed by the 12 different solvers. And in orange, you see the laboratory measurements. And you see like a quite big deviation a bit between the simulation and the measurement. And if we are now using both boundary conditions, so second order and sharp corner, we can get closer to the laboratory measurements. There is still a gap, so it's not ideal. But as I said in the beginning, there's always the question of field of view and segmentation. And for this, we cannot be sure that we satisfy the other two conditions. So let me summarize my talk. Relay solver now supports sub-voxel resolution for flow simulation. We have two new mesh refinement criterion, the posteriori error bound, where you can really specify the error that you want to accept. We have a Reynolds-based mesh refinement criterion where you can use the local Reynolds number to guide where refinement should happen. We also did first implementation steps towards transient Navier-Stokes, and we will also do more in the future. I showed you some validation for the Kalman vortex treat. And last but not least, I showed you new advancements when it comes to no-slip boundary conditions, and I showed you what you can do with it. And yeah, all these new improvements aim to enhance the simulation accuracy. Yeah, what we want to do in the future, we want to do more work towards transient Navier-Stokes. There are also things we can do to improve the accuracy, even without implementing something like large eddy simulation or Reynolds average Navier-Stokes, but we may also implement this in the future. And this brings me to the end of my presentation. Thank you for your attention.